All right, so now thank you for tuning back into the conclusion where we reveal the hidden mystery of where we went wrong in the calculation. Let's remind ourselves what we're considering here. The equation of motion that's going to be useful in analyzing the y direction is going to be one of our equations, uniformly accelerated motion. The displacement in the y direction is equal to the initial velocity in the y direction times time, plus 1/2 the acceleration in the y direction times time squared. So this is sort of like a general form of the equation for what's happening in the vertical direction. All right, and so the 37 balcony is 5 meters above the ground. This roof, the ceiling is 3 meters above the floor, to give you kind of an idea. Like from the floor to that ceiling is 3 meters. I'm about 2 meters tall, just under 2 meters, 197 centimeters tall. Okay. So we're going to let this displacement, the net change in position from where we launch it to where it lands, even though it's going to go up higher than that, because I'm going to throw it up in the air. Okay. This is the added level of difficulty. I'm just going to throw it sideways and let it fall. I'm going to throw it up in the air. It's going to go up to some height above, where I throw it from, but it's going to fall and be a net change in position of 5 meters. Okay. So the displacement is going to be -5 meters. -5 meters. Because down is going to be negative. This is the acceleration I'm going to use. We're going to do this here on Earth. All right. The initial velocity in the y direction, I calculated earlier today that when I throw a ball thusly class, okay, it's 5.2 meters per second. How do I know? Because I did h equals 1/2. No, I didn't. My bad. I did v equals u plus at. And I said, I know that gravity slowed it down to a speed of 0. How fast did I throw it? If -9.81 meters per second squared of gravity, slowed it down for a time that I could measure. So I just timed how long it took the ball to reach maximum height, or how long it took to land back in my hand, divided by 2. That was the time when the velocity was 0. And so that gave me, 5.2 meters per second. So you can figure out how fast you throw something. It's the speed of your throw up. Not if it hits the ceiling, doesn't count, okay? We just need gravity to be the force. So the speed of my up throw, the throw directed upwards, the speed of my throw up. Yeah, nothing wrong with that. The speed of my throw up is 5.2 meters per second times t. So that's the initial velocity. Yes.
Why would it be a negative in front of the 9.81?
It's negative because I'm throwing the ball upwards, which I'm calling positive, and gravity opposes it.
Okay.
So yeah, in general, the equation is plus, but if the acceleration vector is negative,
Okay.
that's where that negative sign came from. So I forget what the time was, but it was like, point, whatever works out to be 5, like 0.5, something like that, about half a second. All right, so we could calculate using another equation of motion, how fast did I throw a ball upwards? So here we know that 1/2 -9.81 times t squared. Let's forget the fact that, meters per second squared, they're all SI units, so it's all going to work out when I solve for t, which is what I want to do. We'll get seconds of time. Okay. All right. How are we going to solve this for time? I'm going to rewrite it over here. 1/2 of -9.81 is -4.905 t squared plus 5.2 t. I'm going to add 5 to both sides. So like I've got this term, -4.905 t squared plus 5.2 t. And then if I add 5 over here, I'll have plus 5, on this side with these guys. And it all would equal 0. Everybody see where I'm going with this? As long as there are no follow-up questions, yes, we perfectly see what you're doing. No explanation is needed. All right, so you're good. You're off and running. Go ahead and finish. For those of us that don't quite see it yet, maybe that would help. So we have some variable we want to solve for, like in algebra class, we call it x usually, and here it's like we care what does this actually stand for, time, t, okay? But it's the variable we're solving for. There's a coefficient in front, you know, it's the standard form of a quadratic equation, x squared plus bx plus c equals 0. So here is our coefficient a, the one belonging with the squared variable. Here's our coefficient b, 5.2, belonging with the variable that's just, you know, to the first power. Our constant term c plus 5 equals 0, right? Because I put everything over on one side of the equation. Who remembers how to solve an equation like this? The quadratic formula. Does anybody remember what that is? All over 2a, there it is. Okay, so if you remember that, then that's what we have to do here. All right, but instead of x equals negative b plus or minus the square root of b squared minus 4ac over 2a, we do t equals all of that. All right, and we just kind of, you know, it's easy to kind of see like correspond these coefficients to that. So we're going to say t equals negative b, right, or opposite b, I think what he said. So t equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So that's what we need to solve. 5.2 squared, so like we'll begin at 25. 5 times negative 5, negative 25. Let's use our calculator. .2 squared minus the quantity 4 times negative 4.905 times 5 equals negative 5.2 plus or minus the square root of, I get 125.14 underneath the radical. 2 times negative 4.905 is negative 9.81. And there you see it. We forgot the negative in the denominator this morning. Let's see what effect that would have on our answers. The square root of 125.14 is 11.2. So we have negative 5.2 plus or minus 11.2 over negative 9.81. It's easy to forget that negative. Here's what I did this morning. I said, oh, we just halved this 9.8 here to get this 4.905, and now we're doubling it again. So I just kind of in my head went, oh yeah, it goes back to 9.81. And I completely forgot that, oh yeah, it's a negative here, right? So I dropped this negative sign. Negative 5.2 plus 11.2 is about 6 divided by negative 9.81 gives us one answer, time to be negative 0.61 seconds. It might take negative 0.61 seconds for the tennis ball to hit the ground. The other solution is negative 5.2 minus 11.2. So we have negative 5.2 minus 11.2. That's negative 16.4 divided by negative 9.81 gives us an answer equals positive 1.67 seconds. So the tennis ball either lands on the ground after negative 0.61 seconds have elapsed, or after positive 1.67 seconds have elapsed. Which do you think is the more reasonable hypothesis if we were to go actually put this to the test out there? Why? Can't have negative time, maybe. I don't know. I'm not so quick to give up on that. Yeah, I mean, let's just think about it mathematically for a second. When we like in math class, this is a parabola, right? And if it crosses the x-axis at 2 points, those are called like the zeros of the function. So it's kind of like in the abstract math world, that, time axis is this way, right? Like if we throw this in as a function of time, it's going forward. But if we were to like plot it, like this parabola as a function of time, it's like, oh, there's a solution back over here in negative time, right? Like where it's going to hit the ground back here at negative 0.61 seconds. We launch at time 0. And so it's kind of cool to be that, yeah, it doesn't make sense in reality, negative time, but just sort of mathematically in the abstract, it's like, oh, it completes the parabola. And I can kind of think about, I could go back in time, like I throw this up in the air, it's going to land on the ground over there in positive 1.7 seconds, 1.67 seconds. But back in the past, 0.61 seconds behind me, would have landed. Anyway, kind of cool, right? You get two solutions, and yeah, you discard this one. You say that's kind of negative time, right? It's got to be 1.67. But this morning, I didn't have the negative sign here, so I calculated what? This one to be positive, this one to be negative. We discarded this correct solution, like, oh, it should land in 0.61 seconds. And I even went through a whole explanation, talking about Newton's cannon over here. If you throw something really fast, like Newton reasoned back when he wrote his Principia, you put a lot of gunpowder on in a cannon on the top of a tall mountain, and you could launch it fast enough that as it fell under Earth's gravitational influence, the Earth would like curve away from it. Because every 8,000 meters you go sideways, Earth drops down 5 meters. And 5 meters is the distance that something will fall if you allow it to fall unhindered for 1 second in Earth's gravity field. So I kind of already knew that, and it's like, wait a minute, this is 5 meters. If I drop the ball, it should land in 1 second. How did I get less than that? So it's like kind of like already suspicious about the incorrectness of this answer. So like if you drop the tennis ball from the top of this ceiling, remember it's only 3 meters, it would hit the ground in less than a second. Imagine racing like gravity, like you do a 40-yard dash. Well, what if you let somebody like accelerate the way gravity does in a race? Like how quickly could gravity sort of cover, a 40-yard dash? Let something go in the influence of gravity. Gravity is a pretty quick accelerator, right? It accelerates things pretty quick on this planet. Every second something falls in the gravity field, it picks up about 23 miles per hour of velocity. Okay, so this is how you would use the quadratic formula to solve for time in an equation like this. If we have a non-zero velocity, we kind of have to because the t is connected to both of these terms. The way around it is to calculate the time to here, and then just consider an object that fell this distance, right? And then at this point, remember, it reaches a temporary speed of 0. So if you like broke it down into sort of 2 steps of the calculation, you could say, well, it's actually 3 steps because you have to calculate 1, the time to get from here to here. You have to calculate this added height that you've covered, plus the 5 meters that you're already up, right? With this one, we just say, hey, I know my net change in position is 5. There are values of t that I could plug in where this term isn't negative enough yet till I cancel out this. And so we'll get answers that are positive all the way here, right? Like we're gonna get a positive displacement if we were to plug in the time to max height. If we were to plug in the time here, here, here. This term is still gonna dominate. We'll still have a positive sort of answer here. As soon as gravity sort of overwhelms that, once they become equal, then we're back to 0, right? Like there is a point right here where this answer is 0. There's a time that this term, the negative term here, cancels out this positive term. That would be right at the point where we launched it from. But then it keeps on speeding up, right? And that's when this term sort of overwhelms. As time gets bigger and bigger, right? This is going as time squared. So eventually this term sort of dominates, and then we get negative sort of answers for our displacement. Okay. So it's nice to have an equation. You can plug in t, any value of t, and you can calculate like what's the height, what's the vertical displacement at that time t. We know at 1.67 seconds, it's all the way back to the ground, negative 5 meters below where it started. If we dug a hole, we could put in bigger values of time and say, well, how much faster, how much further, would it go? All right, so take care of the negative signs, right? It's easy to sort of, like there's a lot going on there, and it's easy enough to sort of drop that negative. And so that's the solution to the mystery. This was our answer that agreed with our measurement. Like we measured the time that it took. It was higher than, it was like 1.5 seconds. And So it's like, then it makes sense, right, if you do the math right. All right. Any questions on projectile motion?